Okay, let's go ahead and practice some of these graphing quadratics, some of these problems. Today we're in section 1, we're really just looking at the effect that A has on the graph. So that, remember we said that A is the leading coefficient, and I want you to notice about these two problems that they don't have a B value or a constant. That's how we know that we've only adjusted the A value. When we do that, remember A controls how the graph opens, so whether it opens up or down, and it's also going to control whether the graph has been stretched or shrunk, so wider or skinnier. Let's go, everything else about this graph will stay the same. So let's start with this piece here that's called the vertex. In these problems, when we've only changed A, the vertex will stay at 0, 0, just like the parent graph. This is not always going to be true, but it will be for today. So our vertex is at 0, 0. Now, let's answer some of these questions before we sketch our graph. The A value is 3, that's that leading coefficient. Because 3 is positive, how is our graph going to open? Yes, it will open up. And if my graph opens up, then my vertex, 0, 0, is going to be a low point, or the lowest point on the graph. That's why we call it a minimum. Our axis of symmetry will always match the x value of our vertex. So our axis of symmetry, remember that's that imaginary vertical line through the vertex. So our axis of symmetry is that x is equal to 0. If you need to prove it to yourself, you can either use Have x to remind yourself that vertical lines have equations where x is equal to a number, or look at all those points there. What do they have in common, or what do they share? Their x value is 0. In this problem, our c, our constant, is 0. So our y-intercept is at the point 0, 0, because it's always going to be 0, comma c. Now these are kind of odd. It's the beginning. Nothing else has been changed. We're going to see some different values as we start moving forward. Now when we do our table of points, I think I changed this on yours, but maybe I didn't. On your table of points, because we have that axis of symmetry, if you always put as your first value your vertex, so in this case 0, 0, I'm pretty sure I put the word vertex in for you, but maybe I didn't. So our first point on our table of points is 0, 0, or our vertex, and then we can just count up or count down, whatever feels easier. In this case, counting up should feel easier. Now our table of points, remember, might have more values than we can actually fit on our graph paper. Our work in this case, remember our problem says y equals 3x squared. So we need to do 3 times 1 squared. Remember, you always do exponents, then multiply. So 1 times 1 is 1, times 3 means my y value is 3. So that really, positive 1, 3 is here on my graph. But since this is a line of symmetry, right, I can do that butterfly fold, those fun paintings, and put in that other point at negative 1, 3. If it's easier for you to see it, maybe here in the x value, you could really think of this x column as being 2 at once. So that negative 1 and positive 1 both have a y of 3. Let's do 2. 3 times 2 squared. Always exponents first, so 2 times 2 is 4, and 4 times 3 is 12. So that we would do 2, no, 12 doesn't really fit on our graph. That's 10, 11, 12. So I can approximate it. It's about here. And when I did my line of reflection, reflect that point across the axis of symmetry. If that reflection doesn't work for you, remember that from your vertex you can count up or you can count down. So negative 1, negative 2, negative 3. Right? Whichever way you go, they will both have the same output. Now we know that this next point won't fit on our graph, but let's go ahead and practice with it just to make sure that we get the right value. So we do exponents, 3 squared, 9, 9 times 3 is 27. That definitely doesn't fit on our graph. So the last thing we need to do is we need to connect the dots. When you connect them, make sure that you do not draw a V. It's a curve, not a V. So make sure you have a U and not a V graph, even though my picture here seems to look a little V-ish. All right, let's practice with number 2. I think you can fill in a lot of this, so I'm not going to talk as much through it. Y equals negative 1/4 x squared. Leading coefficient is the A, so negative 1/4. It opens, in this case, because A is negative, it's going to open down. That means it looks like this, which makes that vertex point a high point or a maximum. In these problems where I've only changed A, my vertex hasn't been adjusted. I've only played with how the graph opens and its width. So my vertex is still at 0, 0. My axis of symmetry is always x equals, and then whatever the x value of the vertex is. So in this case, I still have this picture. My c value is 0. So my y-intercept is 0, c. So 0, 0. Again, vertex is not always y-intercept. It happens in this problem. It's not an always. My table of points, that has an always. Our first value is always 0, or rather, our first value is always our vertex. It's where we always start, because there's only one of those. Always start at your vertex, and then you can count up or count down. So if we counted up, we would be at 1, 2, and 3. But the line of symmetry says that we could also count down. So we could also have negative 1, negative 2, negative 3. Now we need to plug those values in. Now this is where my values that I've chosen might not be the best ones to have picked. It's a fraction. And just like when we had fractions with lines, we might want to apply those same rules to parabolas. So if you don't remember, let me remind you, we use multiples of the denominator. So using 4, 8, and 12 might make better sense. So I would use negative 4, negative 8, and negative 12 because I have a fraction, right? It never matters what x values you choose, so choose the ones that make the problem stay easy. Plug it in. Negative 1/4 times 4 squared. 4 squared is 16 times negative 1/4 should give you a negative 4. So at positive 4, negative 4. At negative 4, I also have negative 4. The axis of symmetry reflecting our points. Let's go to that next value. Negative 1/4 times 8 squared. 8 times 8 is 64, times negative 1/4 is 16, right? Should be. So it should be a negative 16. So at 8, we're all the way down at negative 16. That's way down here. We can kind of estimate how to put those in. Now you could have graphed negative 1, and then you get negative 1/4, positive 1, you get negative 1/4. If you do 2 squared, we end up at 1, or rather at negative 1. So you have all these other values that you could fill in. I just picked the ones that keep the problems the easiest. So I just filled in some extra points, filled them in. I did negative 1/4 because my table wasn't all that I wanted, right? Times negative 2 squared. Just filled in some extra values so that I could have this parabola sketched in nice and neatly. So that brings us down here to the part where it asks us about how does this graph compare to the parent graph. And hopefully on this one where a value is 3, you notice that the graph was skinnier, or maybe you said narrower. We like to call that in algebra a vertical stretch because the graph is stretching away from the x-axis. And in the second problem, where the where the a value was negative 1/4, I hope that you saw that the graph was wider. We like to call that a vertical shrink because the graph is getting closer to the x-axis. In general, the a value, when a is greater than 0, the graph is a stretch of the parent graph. When a is between 0 and 1, or between negative 1, yep, it's between negative 1 and positive 1, the graph is going to be considered a vertical shrink of the parent graph. So if it's fractional, right, whenever we have that fractional value. And when a is less than negative 1, so again, we go back to that whole number, right, bigger than 1, we're going to go back to stretch. But now that the a value is negative, instead of opening up, my graph is going to open down. So the a value affects both what the a value affects. It affects how it opens, it affects whether it's been stretched away from the x-axis, or if it's shrinking closer to the x-axis. This opening is also tied to max and min. That a value is a very powerful value. So a value affects how it opens, right? We call this opening up and opening down. A parabola that opens up has a maximum. A parabola that opens down has a minimum. A graph is said to be stretched in comparison when it gets skinnier or narrower. And it's said to be shrunk when it looks wider. That should bring us to the end of section. Oh, nope, there's some practice problems here where we affect our C value. I'm going to do that in a separate video.